The title of my mini course is Differential Equations, Geometry and Arithmetic. So that's about, huh? Yeah. So before I start, let's speak my credo. I believe differential equations are extremely nice and beautiful. The subject is very deep. And differential equations do know much more than we suspect they could know. And I will, during the lectures, try to illustrate this principle. But I want to introduce my subject by mentioning the only identity I know that made it into Hollywood, and it stems from the movie by The Man Who Knew Infinity about the life of Ramanujan. And there is a scene in that movie where the teacher in Cambridge writes down the following integral. And everyone in the classroom is making notes except Ramanujan. The teacher is irritated by the behavior of Ramanujan. Oh, you don't have to write it down. You come in front of the blackboard and tell me what it is. And then Ramanujan takes the chalk and writes the following series. Sorry, he did not miswrite. Writes this series, and then in the movie, then the teacher is even more irritated, and he says, "How did you know?" And Ramanujan answers, "I don't know, I just do." And then he's thrown out of the lecture room. So if you also only do, well, you may stay. I will not throw you out. So the question is, what is this about? Is this, apart from being a beautiful identity, what does it tell us? What is it about? I will in fact use a slightly different form of this integral, more suited for algebraic geometry, and look at this integral, and it has a very similar expansion. Same coefficients. No, it was right. Sorry. And here we get, so here it's only in squares. So we have this identity. And now, what does it signify, or what is it interesting? And now that depends on who you ask. So we are here in Erwin Schrödinger Institute, so let's ask a physicist. And then the physicist may say, well, I know this integral. I know if you have the pendulum on a rope of length L and a gravitational constant G, then it starts swinging, and the period of the swing, the time, is, this is the formula for the pendulum time. For small angle theta 0, and then it starts moving. And here the time is in first order independent of the initial have the angle, but in fact it is exactly the same series. Plus so it is essentially the same series. So if we write this as pi times ft, call it ft, so this is just 2 pi over g times f time squared delta 0 over 2. So I put this on the exercise sheet. I've seen the exercise sheets are very simple. I will make them more complicated to write. More work to do. So this function starts from physics. Maybe. That's what physicists might answer you. But then you ask your colleague from analysis, because it's an integral, and say, well, that's our business. And then he says, well, it satisfies a differential equation, it's just a special solution. To the so-called Legendre differential equation. And this Legendre differential equation can be written in this form, where theta is my notation for the logarithmic derivative. So this is what the analyst is telling you. So this function is well known, and it may also add that there is a second solution. G t is logarithm t times ft plus some holomorphic series. So there is a second solution to the same differential equation, which develops a logarithm, which in fact shows immediately that this power series cannot be algebraic, because if you do an analytic continuation around the origin, the logarithmic term will prevent that it is of finite order. So this is what your colleague from analysis may tell you. But then you ask, or the numerical analyst who is standing next to you is telling you, well, this formula is completely useless, because we have very better ways of evaluate this numerically, and this series converges slowly, so forget about it. And then if you ask an algebraic geometer or an algebraist, then of course you get another type of answer for the algebraic geometer. We'll tell you, oh, but this is, look at this is the square root of something, this is an integral of an algebraic function. So in fact there is an algebraic curve. There is a curve depending on the parameter t, and the equation will be given by the equation x minus 1, x minus t. So if we would take this equation, we would end up with a slightly different equation. And so you have this curve, and then what is written there is just integral, period integral for this elliptic curve. So if we make a picture of this elliptic curve, we have zeros of this polynomial, 0t, 1, and it will have a loop, and it will have an unbounded part. So this is the real picture of this curve. The algebraist will immediately say, well, this is a polynomial. This can be considered over any field. So this is an element of the k, t, x, y. And the field doesn't even This could make sense in any field. But here we take the real picture of the curve. It will look like that, very well known. And what we're integrating over is integrate from 0 to t. So it's integrating here. And what do we integrate? We integrate a holomorphic differential. Omega t is the residuum. Like the 2 form. So this is our f. Well, it also depends on t, but doesn't matter. So this is the same as dx divided by the partial derivative of the polynomial by y, so it will be over 2y. And so this is the differential, and it is a holomorphic differential. And in fact, what we are having is that we're talking about the integral delta t, omega t, where delta t is this small loop of the curve, and omega is this one form. So it's what is called a period of this differential form. Now you will have the topologist who will say, well, you can look at the real numbers, but let's look at the complex numbers. So what is the complex structure of this equation? Of course, it's a Riemann surface. And the Riemann surface is the Riemann surface of a torus. Here you draw the torus. Well, this branch goes to infinity, so there is one point of this curve in infinity. So if in reality, if you remove one point, and then this loop is really a loop on the Riemann surface. And so we have a cycle in H1 of this curve. It can be considered as an element in the first homology group, this group of 1 cycles. And omega t is a differential form. It's a closed differential form, and it might be considered as a de Rham homology group. And then this is just a pairing between homology and cohomology, and so that's the sort of story you're getting there. And well, but there was also a combinatorist in your department, and he's saying, well, look, 2, 4, 6, so the end coefficient, this is just 2n over n divided by 4 to the power n. So it's really a binomial coefficient what you've written here. You can also see it as the binomial coefficient minus a half n. And then, so if you took f16t, you would get the series 2n n squared tn. And this is now a power series with integral coefficients. So it's even a convergence, of course. So by replacing the variable, by introducing the Eisenstein constant 16, your power series gets integral coefficients. And so these numbers, so it's a generating series of something. And then we'll say, well, there are probably many interpretations of this number, but one of that is we're counting paths in Z2, starting from the origin and then going So it is a little bit different from what Julien was doing this morning. It's a simpler problem. We just count, let's say, the origin. And you do steps in the x and in the y direction. And so you may write it as take the nth power of this Laurent polynomial and take then the constant term of it. This will be just 2n over n squared. So it is counting the number of paths in the plane, starting at 0 and returning after 2n steps. So that would be a story which people tell you then. And of course, this is all correct. It's all true. And there is one last story I want to add to this. Now, you ask a number theorist. This is always the most dangerous. So, what he tells you, well, this is very interesting identity. So, if we look at the following function, just and then this coefficient, so this is a polynomial, so it's just with rational coefficients. In fact, there is only 2's in the denominator. Plus, and then the coefficient t minus 1. So we could cut the series. And then the following is, I think, a remarkable theorem, which goes back to Deuring, 1935, is saying that this truncated hypergeometric series is, in fact, is related to the algebraic geometry of this curve in the following way, that the number of points of this elliptic curve, with now I look at the points in the finite field, that this is expressible in the following way, minus times h d t mod t. So we have a congruence. So this is an integer. This is a rational number. So I think here we need p bigger than 2. Fine. And so the number of points of the curve in the field Fp can be expressed in the period of the elliptic curve. This period function, you can take any t. T is in t. Maybe we need that elliptic curve for that t is non-singular. Et non-singular. Let's put the t0 then. I think it doesn't really make a difference. So The differential equation, this Legendre differential equation, it has two solutions, as I told you. There's two solutions. The one is the series ft, or any multiple of it. And then there is another solution which has a logarithmic term, plus a power series here. And in fact, the topologist at this point will also point out to you that, of course, you have this torus, you have this cycle, which, by the way, for t equals 0, the cycle gets contracted to a point, this delta t. This cycle gets get contracted to a point, it's called a vanishing cycle. So for t is 0, the elliptic curve degenerates. Yeah, you get a repeated root, you get, for t equals 0, you get the equation y squared is x squared, 1 minus x minus 1. And the real curve then looks like a dot. So this loop becomes smaller and smaller. But there is another cycle on the Riemann surface. Let's call it gamma t. And this is delta t. Up to this constant pi will be the holomorphic solution, and the integral over the other cycle, which is sometimes called the co-vanishing cycle. It gets pinched in the limit, and now you can do a local analysis of the integral, how it behaves, and then you will see immediately that it develops the logarithm. This is an exercise which I will put on the... sorry. And this is G. This is the second solution. Yeah? It is. Yeah. Yeah. But what you have, you consider t as a parameter. If t is very, very small, the one cycle, the delta cycle, is almost, is very short. This is a long cycle. If you go for t from 0 to 1, the role of the two cycles becomes interchanged. Then the other cycle becomes small and the other long. Upon analytic continuation, these of course can be transformed in each other. This is an irreducible operator. So there is the space spanned by f generates the whole thing. The space generated by G, of course, also. So, yeah. What I wanted to tell you. Now not. So this is a interesting thing. So Doring was working with Hasse in that time, Helmut Hasse, who was interested in counting finite the numbers of points on curves. And Doering and Hasse Arbeit worked on it. And Hasse proved that in general, the number of solutions for an elliptic curve over, say, FP, over finite field. You count the number of solutions to your equation. So in this case here this is so you can readily just count this, write a small computer program, and then count them, and you can also evaluate this on the computer, and you would see it's equal. We will, in the exercises, show that why this is true. It's not difficult to prove. But Hasse, and that's more difficult to prove, showed that in general the number of points on the elliptic curve is always in the form 1 plus p minus AP, where AP is the trace of a certain operator on a two-dimensional vector space, which is basically the H1 of the elliptic curve. And the size of this term AP is always smaller than square root of p. So if you look at the number of points modulo p, it is basically the same as looking at AP. But knowing AP gives you an answer for the number of points, not mod p, but just as an integer. So this result, which gives the number of points modulo p only, is in fact determining the number of points of the elliptic curve itself. And this means that the differential equation, this Legendre differential equation, this one, knows the number of points of the elliptic curve because it knows its only holomorphic solution. This is a unique solution around the origin. The expansion is unique. And that power series evaluated mod p, basically, gives the number of points mod p, which for an elliptic curve determines the number of points itself. Yes, but we take a power series which starts with 1, because f was 1 plus. Yeah. So it's unique up to scalar. And if you look at the analytic period, there is a factor pi in front of it, which is not playing a role here. This pi is sort of taken over by this same sign. Okay. But this is a result. So Doering, counting the number of points mod p is the same as computing the Frobenius trace mod p. And this is much easier than without the mod p. And Doering does that calculation and finds this answer. But it is not remarked at that time that this is the truncation of the hypergeometric solution to the holomorphic solution of the Legendre differential equation. That was later by Iguza. He used that fact to show that this polynomial, which is the Hasse polynomial, it is called, The Haas polynomial has all the roots different, has no repeated roots, because it's a solution of the differential equation mod P. And then, so what is the aim? What was the aim? The aim, well, first of all, why is there a relation between these things? So why? And then generalize. First of all, you may say, well, we want not mod P, we want mod P squared, mod P cubed. We want to lift it to the p-adics. I think that Masha and will speak on this very much. So mod P squared. Although, as I remarked, that in this example, it really doesn't give more information because the result mod P already gives the integers. But for in others, two higher dimensional. Other varieties, other. Elliptic curves, so higher dimension. So, and this is very much what Dwork in the early 60s then started doing, and he gave a formula for the unit root of the Frobenius. So this is an operation on a two-dimensional vector space. It has a characteristic polynomial. This is the characteristic polynomial of Frobenius. And Dwork gave a formula for the p-adic roots of this polynomial in terms of the hypergeometric function. I suppose we are going to hear about that. But then it was realized that the right framework is to understand and describe these things was p-adic homology. And so there were p-adic homology theories developed. Maybe the first after Dwork was the Monsky-Waschnitzer. And Marius wrote a very nice paper on, where he also explained this in great detail about how Monsky-Waschnitzer homology can be used to prove these things. And, I think this will be covered by the other course. So my direction now will be higher dimensions, and in particular, so-called Calabi-Yau varieties. And in particular, threefolds. And it is so that one can, starting from the differential equation, well, in certain situations, you can determine the characteristic polynomial of Frobenius. I will explain what it is for high-dimensional varieties. A lot of these things are conjectural, but the statements are completely elementary. And I want to give these statements. Not everything is proven, but we have a young audience who can set out to prove certain statements I will make. Yeah, no, it will take longer. So this was the motivational part. Now I will would like to tell a little bit about differential equations, hypergeometric differential equations, and in particular, properties like singularities, the Riemann symbol, which will play also a role in the local monodromy and the global monodromy, things like that. So that is my first. So this is now rather well known, but as the Legendre differential equation is an example of a hypergeometric equation, you may as well recall certain basic facts about the hypergeometric equation and the way how you can generalize things. Oh, by the way, I forgot to tell what happens if you ask this a historian. We have a historian of mathematics in mind. He, of course, will say, oh, everything is in Euler. And that is true also. So you know, a geometric sequence going back to the basics. Any term, the next term is multiplied by a constant, so an, the nth term will be you get a geometric sequence. And now the hypergeometric well, you just let this constant depend on n, where mn is a rational function. The parameter n. Now this was first appears in the book by Wallace, 1655. So it's a very naive idea. It's a generalization of the geometric sequence, is the hypergeometric sequence. And John Wallace. So this is before calculus was invented. Before Wallace. Or one of the first writers. So this is. Book. What is the title of the book? Forgot. So, as an example, you have just the sequence where this is a linear function, say alpha plus n times an. So rather than if alpha is 0, you get basically factorial. So this is the next sort of factorials. And this particular one, of course, if you do this, the an is alpha n times a0, where this alpha n is the Pochhammer symbol. It is alpha plus 1. Plus n Pochhammer. So this notation is from the 19th century, but the ideas are much older. And then hypergeometric series will be just a generating series of such a hypergeometric sequence. And of course, you find many examples of hypergeometric series. This is in fact the geometric series, but also t squared t. So this is basically the logarithm. And here, to go from 2 to 3, so here you, of course, have a n plus 1, basically, n plus 1, n. So you have a rational. So if you differentiate or integrate your series, it stays hypergeometric. You get also a hypergeometric series. And of course, the series Julien was talking about this series. This was studied by Euler in great detail. We even evaluate this function at t is 1, get the right answer. And of course, things like this, the exponential series, but also if you have two hypergeometric series and you do term-wise multiplication, then it's still hypergeometric because of property. So you have this squared this is already lesser known, the Bessel function. And you have this. And of course, also this one plus a half t. Well, we've seen this. So here, of course, a n plus 1. And an is this what we had before, is this half n. The central binomial coefficient. And if you do coefficient squaring, we get our series from the beginning. So this one is, well, it's minus a half over n. So this is really just the development of the square root function. And then maybe very well known other b plus 1. So this is the Euler, but people call it Gauss hypergeometric function. You find in the work of Euler all the different properties which were known and became popular in the 19th century. You find them really in Euler's work, including the continuous fraction, which is ascribed to Gauss, but it is all in Euler. Gauss got famous because he wrote a beautiful paper explaining all the properties in a systematic way. But at points he forgot to say that these things were known. So people in the 19th century started talking about the Gaussische Reihe. So Riemann does it. We call it the Gaussian series. But so this is a hypergeometric, because at each step you multiply the previous result by a rational function of degree 2 in the numerator and degree 2 in the denominator. And so let's agree, call it the Euler-Gauss hypergeometric function. Then the ultimate generalization, this is now called the generalized hypergeometric function. And the notation you find is something like this. T sum alpha 1. So here you do these Pochhammers, alpha P, and here the Pochhammers in the denominator. P and Q. And then there is one factor where you sort of take beta is 0, because you want to that this series starts by 0, so you have to take care to include 1 factorial. Now this is a hypergeometric series, because Pochhammer symbol is hypergeometric. And it's just a product. And so that's sort of the most general one. And the hypergeometric differential equation, where we'll have to do with it. Differential equation. So this is most easily expressed again in this operator d dt. There's a logarithmic derivative. And then if you remark that if you apply this to the polynomial t to the power n, it just multiplies by n. So if you apply it twice, you just get this. If you take any polynomial then it's the polynomial evaluated at n times t. So the t to the power n is an eigenfunction for the eigenvalue n. This is very convenient. And if you now look at P0 and P1, two polynomials, and you write the following. Better. And apply this to a series, power series. Then this is a calculation everyone should be doing his hand. So then you get, of course, that an T0n times an times Tn is T1n an Tn plus 1, because there is this extra T here. So if you apply this to this, you get here Tn plus 1. If you now compare the coefficients for T to the power n, you will get that an plus 1 must be P1. So you see from this calculation, if an is hypergeometric, then the generating series is annihilated by this differential operator. And conversely, that if you have this hypergeometric series is annihilated by that operator. Okay. Good. So, in particular, the operator annihilates the series an, where an solves the recursion. So you have a direct link between differential operators here with two terms. If you use the notation theta, the operator becomes very simple. If you want to write it out as in the ordinary form of a differential operator, you have to calculate what happens if you do twice logarithmic derivative, and then of course there are more terms, you generate more terms, and your differential equation becomes more complicated. But this is the simplest way to write the hypergeometric differential equation. And let's do it for the hypergeometric series f a, b, c, t. So this Euler-Gauss, this is f with parameters a, b, and c. And okay. And what you see is that satisfies the differential equation theta plus a zero. So you see that the upper Pochhammer indices come here, and the lower Pochhammer indices come here, but with a shift by 1. Here. And the reason for the shift by 1 is, of course, this t. So I did in the calculation. But it's particularly simple to remember, and similar to my generalized hypergeometric series. So this is the series which is still here. Then it is a direct generalization of this case. You have more Pochhammer symbols, and so you find the standard hypergeometric I minus 1 here it's 1 up to p. Here's I is 1 up to 0 up to q, where beta 0 is 1. So you get, like here, you get 1 factor theta, which corresponds to the fact that you have this factorial here. So you get a power series expansion. If you would write here theta plus something else, then there would not be a power series expansion, with integral powers around the origin. But the hypergeometric differential equation, of course, also exists without this condition. It's differential, but it does not have a power series expansion of that type. This is a small thing to keep in mind. So this is the hypergeometric, generalized hypergeometric differential equation. Yeah? Come to that now, because that's really the big insight of Riemann, who first, I think maybe Gauss also understood it, and Euler maybe, but the fact that it is universal, that it is the sort of the only differential, well, the second, this one is the most general second order differential equation with regular singularities and three singularities.